How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You've seen the headlines. You've probably used the tools. ChatGPT, Gemini, Claude, Grok. You type a question, and in seconds you get a poem, a piece of code, a business plan. It feels like magic. It feels like you're talking to a mind. But what if I told you that behind that stunningly human-like conversation, there's no mind at all, no thought, no understanding, no consciousness, just a mirror, a vast, impossibly complex mathematical mirror reflecting all of human language back at us? Today, we're opening the black box. We're going to trace the decades-long journey to build this universal echo, revealing the first principles of how it truly works, not by understanding our world, but by creating a statistical shadow of it. This is the story of how AI learned our language. Our story begins not with silicon chips and neural networks, but with a question posed in 1950 by the brilliant mathematician Alan Turing. In his paper, Computing Machinery and Intelligence, he proposed what he called the imitation game, which we now know as the Turing test. The idea was simple, but profound. Could a machine converse so convincingly that a human couldn't tell it apart from another person? This was the birth of the dream, the foundational quest of natural language processing, or NLP, to build a machine that could truly speak our language. The first attempts to realize this dream were built on a philosophy we now call symbolic AI, or as some affectionately call it, good old-fashioned AI. The approach was intuitive. If you want a computer to understand language, you must teach it the rules of language, grammar, syntax, semantics, just like you'd teach a student. The most famous example of this era was a program developed at MIT between 1964 and 1966 by Joseph Weizenbaum. It was called ELIZA. ELIZA was a clever party trick, a simulated psychotherapist that could engage in surprisingly human-like conversations. If you told it, "My head hurts," ELIZA might respond, "Why do you say your head hurts?" People were captivated. Some of Weizenbaum's own colleagues would spend hours pouring their hearts out to the machine. But under the hood, ELIZA was just a collection of simple handwritten rules and pattern-matching templates. It had no understanding whatsoever. It would identify keywords in a user's input and plug them into a prescripted response, like, "Tell me more about your problem." This rule-based approach is best understood with an analogy. Imagine a librarian with a very strict, finite set of rulebooks. If you ask a question that is phrased exactly as it's written in one of their rulebooks, they can look it up and give you the pre-written answer. But if you ask the same question with slightly different wording, or about a topic not covered in their limited collection, the system shatters. It has no flexibility, no ability to generalize. This is the core problem of symbolic AI. It is brittle. This brittleness stems from a fundamental and ultimately fatal flaw known as the knowledge acquisition bottleneck. Human language is messy, ambiguous, and constantly evolving with new slang and idioms. To capture it with rules, you would need to write a rule for every possible contingency, every exception, every nuance. As the complexity of the task grows, the number of rules required increases exponentially. Manually encoding the entirety of human knowledge and linguistic subtlety into a computer is a fundamentally impossible task. The system requires constant human intervention to update its rulebooks, and it can only ever operate within the confines of what its human programmers have explicitly told it. The early promises of AI, built on toy problems like SHRDLU, a program that could understand commands in a restricted blocks world, failed to scale to the complexity of the real world. The sheer number of rules needed created a combinatorial explosion that early systems couldn't handle. This wasn't just a technical hurdle, it was a paradigm-level failure. The inability of symbolic AI to overcome its own brittleness and the impossible task of knowledge acquisition led directly to the first AI winter in the 1980s, a period where funding dried up and faith in the field waned. The echo at this stage was just a crude recording, capable of playing back only a few pre-selected phrases. It couldn't learn, it couldn't adapt, and it couldn't scale. The failure of the rule-based approach forced a revolution. Starting in the late 1980s, researchers began to pivot away from hand-coding knowledge and toward a new paradigm, statistical NLP and machine learning. The idea was radical. Instead of teaching the machine the rules of language, why not let the machine learn the rules for itself by analyzing vast amounts of text? This shift was powered by increasing computational power and the growing availability of large digital text collections, or corpora. Early statistical models, like hidden Markov models, could perform tasks like identifying parts of speech by calculating probabilities from data. But the true leap forward came in the 2010s with the rise of deep learning and a concept called word embeddings. Techniques like Word2Vec, developed at Google, transformed words into dense numerical vectors in a high-dimensional space. In this space, words with similar meanings were located close to each other. This allowed for a kind of vector arithmetic that captured semantic relationships, famously demonstrated by the equation: the vector for king minus the vector for man plus the vector for woman results in a vector very close to queen. For the first time, a machine was learning the abstract relationships between concepts, not just matching keywords. This new capability was supercharged by an architecture designed specifically for sequential data like text, the recurrent neural network, or RNN. Unlike the models before it, an RNN has a form of memory. It processes a sentence one word at a time, and at each step, the output from the previous word is fed back into the network as an input for the current word. You can think of an RNN as a messenger running along a sentence. At the first word, the messenger reads it and jots down a quick summary. At the second word, they read it, pull out their previous summary, and combine the two into a new, updated summary. They repeat this process for every word. In theory, by the time the messenger reaches the end of a long paragraph, their summary should contain information from the very beginning. This seemed to be the solution for understanding context in language. But RNNs had a fatal flaw, a mathematical ghost in the machine known as the vanishing gradient problem. During training, a neural network learns by making a prediction, calculating how wrong it was, and then sending that error signal backward through the network to adjust its internal connections. In an RNN, this error signal has to travel backward through time, step by step, from the end of the sentence to the beginning. At each step, the signal is multiplied by the network's weights. If those weights are small numbers, the signal shrinks exponentially with each multiplication. The best analogy for this is a game of telephone. The error signal is the original message. At the last word of the sentence, the message is clear. But to correct the network's understanding of the second-to-last word, that message is whispered back one step. Then it's whispered back again and again. By the time the signal reaches the first few words of a long sentence, the message has become a faint, garbled whisper, or has vanished entirely. The practical result is that the network is unable to learn from words that appeared early in a sequence. It has a short-term memory problem. It cannot capture long-range dependencies. For example, in the sentence, Alice, who grew up in France and speaks fluent French, can't eat peanut butter because she has a severe nut allergy. An RNN might struggle to connect the final word allergy to the crucial context of Alice at the very beginning. Researchers developed a more complex version called a long short-term memory network, or LSTM, which used a clever system of gates to help the model decide what information to keep and what to discard, which helped mitigate the problem but didn't fully solve it. LSTMs were still fundamentally sequential. This created two inescapable problems. First, the memory issue, while improved, still lingered. Second, the sequential word-by-word processing meant you couldn't parallelize the computation. You couldn't process the 10th word until you had finished with the 9th. This created a massive speed bottleneck, making it impractical to train these models on the truly massive datasets that were becoming available. The entire history of language AI up to this point was a story of fighting against the limitations of sequential processing. The rule-based systems were logically sequential. The neural networks were computationally sequential. The field was stuck in a timeline, unable to see the whole picture at once. To build a better, more powerful echo, they had to break time itself. They needed a way to hear the entire sentence all at once. The year is 2017. A team of researchers at Google publish a paper with a bold, almost defiant title, "Attention is all you need." This paper didn't just propose an improvement on the existing models. It was a complete paradigm shift. It introduced a new architecture called the transformer, and it threw out the single most defining feature of its predecessors, recurrence. No more word-by-word, sequential processing. The big idea behind the transformer was parallelization. Instead of reading a sentence one word at a time like an RNN, the transformer architecture was designed to ingest and process every word in the sentence simultaneously. This was a monumental breakthrough. It immediately solved the speed bottleneck that had plagued RNNs and LSTMs, unlocking the ability to train models on vastly larger datasets using the parallel processing power of modern hardware like GPUs. But this created a new, profound question. If you're not processing words in order, how do you understand context? How does the model learn the intricate relationships between words that give a sentence its meaning? The answer lay in the paper's title. The central mechanism of the transformer is called self-attention. It's a technique that allows the model, for each word it processes, to look at all the other words in the input sequence and dynamically weigh their importance. It learns context, not by remembering the past, but by creating a rich, interconnected network of relationships between all the words at once. So how does this self-attention mechanism actually work? It sounds abstract, but the core intuition is surprisingly elegant. Imagine you're trying to understand the word "it" in the sentence. The animal didn't cross the street because it was too tired. As a human, you instantly know it refers to the animal. You do this by paying attention to the surrounding words and identifying the most relevant context. Self-attention is a mathematical way of giving the AI this exact superpower. Let's use an analogy of a research assistant trying to decipher this sentence. For every single word in the sentence, the model generates 3 distinct vectors: a query, a key, and a value. First, the query vector. This represents the current word we're focusing on. It's the research assistant's specific question. For the word "it," The query is essentially asking, who or what am I referring to in this sentence? Second, the key vector. Every word in the sentence, including it itself, gets a key. You can think of the key like the title on the spine of a book. It's a vector that advertises that word's semantic role and content. The word animal has a key, street has a key, and tired has a key. Next comes the scoring. The research assistant takes the query for it and compares it to the key of every other word in the sentence. This comparison is done using a mathematical operation called a dot product, which essentially measures the similarity between the two vectors. This process generates an attention score for every word in the sentence relative to it. The key for animal will produce a very high score, indicating high relevance. The key for street will produce a low score. These scores are the attention weights. Finally, we have the value vector. Each word also has a value vector, which represents the actual substance or meaning of that word. If the key is the title on the book's spine, the value is the rich information contained within its pages. To create a new contextual representation for the word it, the model then calculates a weighted sum of all the value vectors in the sentence. The value vector for animal, which had a high attention score, will contribute heavily to this new representation. The value vector for street, with its low score, will contribute almost nothing. The result is that the final vector for it is now mathematically infused with the meaning of animal. The echo is no longer just hearing one word at a time. It's hearing a chorus of interconnected meanings, all calculated in parallel. And it gets even more sophisticated. The model doesn't just do this once. It has what's called multi-head attention. Think of it as a team of specialist detectives, all examining the sentence at the same time. One attention head might be an expert at identifying subject-verb relationships. Another might specialize in resolving pronoun antecedents, like our it and animal example. A third might focus on identifying locations or temporal relationships. Each head conducts its own query key-value analysis, and their combined findings are integrated to build an incredibly rich, multi-layered understanding of the sentence's grammatical and semantic structure. Discarding the sequential nature of RNNs gave the transformer its speed, and self-attention gave it its contextual understanding. But it also created a massive problem. If you process all the words at once, the model has no inherent sense of their order. It would see no difference between the sentences, Alan walks dog, and dog walks Alan. Two sentences with identical words but drastically different meanings. This is a catastrophic failure for any system trying to understand language. The solution proposed in the Attention is All You Need paper is another stroke of genius. Positional encoding. The idea is to inject information about the position of each word directly into its initial vector embedding before it even enters the attention mechanism. It's like giving every word in the sentence a unique set of GPS coordinates. This isn't just a single number. It's a whole vector of numbers generated using a clever combination of sine and cosine functions of different frequencies. Think of it this way. The position of each word is described by a unique blend of overlapping radio waves. The first word in the sentence might be represented by a combination of a slow, steady bass frequency and a fast, high-pitched treble frequency. The second word will have a slightly different combination of these frequencies, the third a different one still, and so on. Because these wave patterns are mathematical and predictable, the model can learn not just the absolute position of a word, but also the relative distance between words. It can learn that bytes is 1 unit away from dog and 3 units away from the end of the sentence. This mathematical map is added directly to the word's meaning vector. The final vector that enters the transformer's first layer therefore contains information about both what the word is and where it is in the sequence. This reveals the pragmatic, problem-solving brilliance at the heart of AI research. The transformer architecture isn't a single, monolithic idea that arrived fully formed. It's a cascade of clever trade-offs and elegant fixes to achieve the speed and scalability needed to train on modern hardware. The designers abandoned sequential processing. This created a new problem: how to understand context without sequence. The solution was self-attention. But processing everything at once created yet another problem: the loss of word order. The solution was positional encoding. The final architecture is a testament to engineering, a series of brilliant solutions to self-imposed problems, all working in concert to create the foundation for the AI revolution. The transformer architecture, with its ability to process text in parallel, was like a revolutionary new engine. But an engine is useless without fuel, and for large language models, that fuel is data, unfathomable amounts of data. The shift to the transformer architecture happened in tandem with the realization that to unlock its potential, you needed to train it on a dataset that reflected the sheer scale and diversity of human language itself, the Internet. The primary source for this data is a project called Common Crawl. It's a non-profit organization that has been systematically crawling the web since 2008, creating a publicly accessible archive of trillions of web pages. This dataset is the raw material, the primordial soup from which many of the most powerful LLMs are born. Models like GPT-3, Llama, and T5 were all trained on massive portions of Common Crawl's archive. In fact, over 80% of the text GPT-3 was trained on originated from this single source. It's difficult to convey the scale we're talking about. The full Common Crawl archive is over 9.5 petabytes. A petabyte is 1,000,000 gigabytes. To put that in perspective, if a single gigabyte of text is equivalent to a pickup truck filled with paper, 9.5 petabytes would be a line of trucks stretching from New York to Los Angeles and back more than 20 times. Meta's recent Llama 3 model was trained on a dataset of over 15 trillion tokens, a token being a word or part of a word. While Common Crawl is the largest component, it's not the only one. Researchers have curated other massive datasets to complement it. The Pile, for instance, is an 800 gigabyte dataset specifically curated for training LLMs, blending text from 22 diverse sources, including academic papers, books, emails, and even computer code from GitHub. Another key dataset is C4, which stands for the Colossal Clean Crawled Corpus. It was created by Google to train their T5 model and is, as its name suggests, a heavily filtered and cleaned version of Common Crawl. This points to a critical, often invisible, part of the process. You can't just dump the raw internet into a neural network. The raw data from a web crawl is a chaotic mess. It's a deluge of HTML tags, advertisements, navigation menus, legal disclaimers, gibberish, machine-translated text, hate speech, and endless repetition. Feeding this directly to a model would be like trying to power a Formula One car with crude oil. The model would learn all the wrong patterns. This is where the unglamorous but absolutely essential process of data curation comes in. It's the complex multi-stage pipeline that refines that raw digital crude into high-octane fuel for LLMs. The first step is aggressive filtering. Curation pipelines employ a battery of rule-based filters to discard low-quality documents. For example, they might remove any document that is too short to be meaningful, or any document that contains an excessive amount of repetition, which is often a sign of spam or auto-generated content. They use filters to remove pages with too many bad words or lines of text that don't end with proper punctuation. The next and computationally very expensive step is deduplication. The Internet is rife with duplicate content. The same news article posted on 100 sites, the same product description on 1,000 e-commerce pages. If a model sees the same text over and over again, it will overfit to that text, learning to memorize it rather than learning general linguistic patterns. To combat this, data pipelines use sophisticated algorithms to find and remove not only exact duplicates, but also near duplicates from the training set. Finally, the most advanced pipelines perform quality scoring. Instead of just using simple rules, they use other smaller machine learning models to rate the quality of a given document. The training process for GPT-3, for example, involved a clever technique. The developers first curated a high-quality reference dataset called web text, which was built from all the outbound links on the social media site Reddit that had at least 3 upvotes. They then trained a classifier model to distinguish between a document from this high-quality corpus and a random document from Common Crawl. This quality scoring model was then used to scan through the petabytes of Common Crawl data and keep only the documents that looked most like the good ones. This entire curation process, the filtering, the deduplication, the quality scoring, is the invisible gatekeeper of modern AI. The quality of the final model is now understood to be dramatically affected by the quality of its training data. But this raises a crucial point. The process of cleaning the data is not an objective one. It is a series of subjective choices made by developers, and these choices are a powerful vector for embedding bias before the model is even trained. Consider the goal: to obtain high-quality text. A popular method, as we've seen, is to filter for content that is stylistically similar to pages linked from Reddit. However, research has shown that this approach inherently favors content that appeals to Reddit's primary audience, which is predominantly white and male. This means that the very definition of quality is being shaped by the preferences of a narrow demographic slice of the Internet, which is then used to train a model meant to serve the entire world. Similarly, the use of bad words lists for filtering is deeply flawed. These lists are often crude and fail to account for context. They can incorrectly flag non-toxic language used by marginalized communities, such as LGBTQIA+ groups, effectively removing their voices from the training data. At the same time, they often fail to detect more subtle or coded forms of hate speech, which then remain in the dataset. The universal echo, therefore, isn't reflecting the universal human experience. It is reflecting a heavily filtered, curated, and biased version of it, shaped by the subjective and often flawed choices of its creators. The distortions begin here. When a large language model is trained on a dataset scraped from the Internet, it does more than just learn grammar and facts. It learns a statistical model of the world as represented in that text. And because our world is filled with historical and systemic biases, the text we produce reflects those biases. LLMs, as mathematical mirrors, inevitably absorb and amplify these societal prejudices, leading to outputs that can be unfair, stereotypical, and harmful. These are not abstract, theoretical concerns. they are documented realities. In the realm of gender bias, models have been shown to strongly associate certain professions with specific genders. Prompts about doctors or software engineers are more likely to be completed using male pronouns, while prompts about nurses or receptionists are more likely to use female pronouns. A famous real-world example was an experimental recruiting tool built by Amazon. Because it was trained on a decade of the company's hiring data, which was predominantly male, the AI taught itself that male candidates were preferable. It learned to penalize resumes that contained the word women's, such as captain of the women's chess club, and had to be scrapped. The problem is just as acute with racial and cultural biases. A landmark investigation by ProPublica examined a risk assessment algorithm called Compass, used in courtrooms across the United States to predict the likelihood of a defendant reoffending. The investigation found that the algorithm was twice as likely to incorrectly flag black defendants as being at high risk of reoffending as it was for white defendants. The model, trained on historical crime data, had learned to replicate the systemic biases of the justice system itself. In language, this can manifest in sentiment analysis tools that are more likely to assign negative sentiment scores to texts written in African American vernacular English, or to associate different demographic groups with harmful stereotypes. When these biased models are deployed in critical domains like healthcare, hiring, and legal judgments, they don't just reflect our society's inequalities. They actively perpetuate and exacerbate them, often under a veneer of objective technological neutrality. The data that fuels these models, the trillions of words from books, news articles, blog posts, and websites, was not created in a vacuum. It was written by people, and in many cases, it is protected by copyright. This has set the stage for a monumental legal battle, a fundamental clash between the tech industry's insatiable need for data and the rights of creators to control and be compensated for their work. A wave of high-profile lawsuits has been filed against major AI companies. The New York Times is suing OpenAI and Microsoft, alleging that their models were trained by illegally copying millions of their articles. The Authors Guild, representing prominent writers like John Grisham and George R.R. Martin, has filed a similar class action lawsuit, claiming their books were fed into ChatGPT's training data without permission. And Getty Images is suing Stability AI, the creator of the image generator Stable Diffusion, for allegedly using over 12 million of their copyrighted photographs to train its model. The core argument from the plaintiffs is straightforward. The AI companies engaged in mass-scale copyright infringement. They copied vast quantities of protected works without a license and used them to build a commercial product that now directly competes with the original creators. The Authors Guild argues that these models can generate texts that mimic an author's unique voice and style, or even produce unauthorized derivative works like summaries or sequels, directly harming the market for their books. In response, the AI companies have mounted a powerful defense centered on a crucial doctrine in U.S. copyright law: fair use. Their central claim is that their use of the copyrighted material is transformative. They argue that they are not simply making copies to create a substitute for the original works. Instead, they are using the text to train a model to understand the statistical patterns of language, the relationships between words, sentence structures, and concepts. The final product is not a repository of books or articles, but a new, functional technology, the LLM itself. This defense leans heavily on legal precedents, most notably the 2015 case Authors Guild versus Google. In that case, the court ruled that Google's project to scan millions of library books without permission to create a searchable database was a transformative fair use. The court found that the purpose of the Google Books project, to enable search and analysis, was fundamentally different from the purpose of the original books, and it did not harm the market for them. AI companies argue that training an LLM is similarly transformative. The legal battle will likely hinge on a critical distinction: the difference between training the model and the model's output. While courts may be sympathetic to the fair use argument for the training process itself, the case becomes much weaker if the model's output is substantially similar to a copyrighted work. If ChatGPT produces a paragraph verbatim from a New York Times article, that is a direct and difficult-to-defend infringement. OpenAI has publicly referred to this kind of verbatim regurgitation as a bug that they are actively working to fix, reinforcing their argument that their technology's intended purpose is generative and transformative, not reproductive. The outcome of these cases will fundamentally shape the economic landscape of the next technological era. If the courts rule in favor of the AI companies and uphold the transformative fair use defense for training data, it will solidify the current paradigm where access to massive computational power and the ability to scrape the web are the primary ingredients for building powerful AI. This would likely maintain the dominance of the existing tech giants. On the other hand, if the courts rule in favor of the creators and require AI companies to license their training data, it would create a vast and lucrative new market for content licensing. However, this could perversely lead to even greater market concentration, as only the most well-funded companies would be able to afford the astronomical licensing fees required to train a frontier model, potentially stifling smaller competitors and the open-source movement. These lawsuits are not just about copyright. They are about who gets to build and who gets to profit from the foundational infrastructure of our digital future. Beyond bias and copyright, there is a third, more personal risk lurking in the vast datasets used to train LLMs, the risk to our privacy. The great scrape of the Internet did not just ingest professionally published articles and books, it ingested everything. Forum posts, product reviews, blog comments, social media profiles. A chaotic tapestry of human expression that often contains deeply personal and sensitive information. Because LLMs are designed to be powerful pattern matching and memorization machines, they are susceptible to a phenomenon known as training data leakage. In simple terms, the model can inadvertently memorize specific, unique sequences of text from its training data and then regurgitate them in its output. Researchers have demonstrated that by carefully crafting prompts, it is possible to extract verbatim personal information that was present in the training data, including names, email addresses, phone numbers, physical addresses, and even medical information shared on public forums. This represents a colossal privacy violation at the most fundamental level. The data was scraped and ingested without the knowledge or consent of the individuals involved. People who shared personal stories on a medical support forum or a blog years ago could never have imagined that their words would be absorbed into a commercial AI product and potentially revealed to a random user on the other side of the world. This issue also highlights a stark hypocrisy at the heart of the AI industry. Companies like OpenAI have vigorously defended their right to scrape the public web for training data, arguing it is essential for innovation. Yet, they have also taken technical and legal measures to prevent others from scraping their own websites or using the output of their models to train competing ICE. This "scraping for me, but not for thee" stance reveals that the arguments about the necessity of unfettered data access are often a matter of commercial convenience rather than a deeply held principle. The echo, it seems, remembers far more than we'd like, and the question of who controls that memory and the private lives it contains is one of the most urgent challenges we face. A freshly pre-trained large language model is an incredible but untamed beast. It is a raw engine of text prediction, optimized only to complete a sequence of text with the most statistically probable next words. It has no inherent concept of being helpful, honest, or harmless. If you ask it a dangerous question, it will likely give you a dangerous answer, simply because that's the pattern it learned from its data. The process of taming this beast and steering its behavior to be useful and safe for humans is known as AI alignment. For years, the gold standard for alignment has been a technique called reinforcement learning from human feedback, or RLHF. This is the process that transformed the raw GPT-3 into the much more helpful and cautious assistant we know as ChatGPT. The process, while complex under the hood, can be broken down into 3 main steps. First, you collect human preference data. This is a massive, labor-intensive effort. AI companies hire armies of human labelers and present them with a prompt. Say, explain black holes to a 5-year-old. The model generates 2 different answers. The human labeler's job is not to write the correct answer, but simply to choose which of the 2 responses they prefer. They give a virtual thumbs up to one and a thumbs down to the other. This process is repeated millions of times, creating a massive dataset of human preferences. Second, you train a reward model. This preference dataset, containing the prompt, the winning response, and the losing response, is used to train a completely separate AI model. The sole purpose of this reward model is to act as a proxy for the human labelers. It learns to take any prompt and a response and output a numerical score that predicts how much a human would like it. A higher score means a more preferred response. Third, you fine-tune the original LLM using reinforcement learning. This is where the magic happens. The LLM is given a prompt from a new dataset. It generates a response. That response is then shown to the reward model, which gives it a score. This score is used as a reward signal. Using a reinforcement learning algorithm like proximal policy optimization, this reward signal is used to update the LLM's parameters, nudging it to produce responses that will earn higher scores from the reward model in the future. Through millions of cycles of this game, generate, score, update, the LLM gradually learns to align its behavior with the preferences captured in the reward model. RLHF has proven to be incredibly effective at making models follow instructions, refuse inappropriate requests, and generally behave in a more helpful and harmless manner. But it has significant drawbacks. It is a breathtakingly complex and computationally expensive process, requiring the training and maintenance of multiple large models simultaneously. It can be unstable, and the process of collecting the human preference data is a slow, expensive, and continuous bottleneck. The expense and complexity of RLHF have driven researchers to find smarter, faster, and more efficient ways to achieve alignment. This has led to a new generation of techniques that are rapidly becoming the new industry standard. The first major innovation is direct preference optimization, or DPO. DPO was born from a clever mathematical insight. It turns out you can achieve the same alignment goal as RLHF without the need for a separate reward model or the unstable reinforcement learning step. DPO starts with the exact same human preference dataset, prompt, winner, and loser, but instead of using it to train a reward model, it uses the data to directly fine-tune the LLM itself. It employs a specific loss function that mathematically encourages the model to increase the probability of generating the winning response while simultaneously decreasing the probability of generating the losing response. It's a more direct, stable, and computationally cheaper path to the same destination, making it far more accessible for smaller teams and more efficient for large-scale operations. While DPO makes the process more efficient, another approach seeks to change the process itself. Developed by the AI company Anthropic for their Claude models, constitutional AI aims to reduce the massive reliance on human feedback altogether. The core idea is to give the AI a constitution, a set of explicit, human-written principles to follow, such as choose the response that is less harmful, or choose the response that is more helpful and honest. The alignment process then becomes a form of AI self-improvement. In the first phase, the model is prompted with harmful requests and generates a harmful response. It is then asked to critique its own response based on a principle from the Constitution and rewrite it to be harmless. This creates a dataset of self-corrected responses that is used for an initial round of fine-tuning. In the second phase, the model generates pairs of responses to prompts. Then, using a principle from the Constitution, the AI itself is asked to choose which of the two responses better adheres to the principle. This creates a preference dataset, just like in RLHF, but the preferences are generated by AI, not humans. This AI-generated feedback is then used to train a preference model and fine-tune the LLM with reinforcement learning, a process Anthropic calls reinforcement learning from AI feedback. This approach offers the promise of greater scalability by reducing the human labeling bottleneck and greater transparency, since the principles guiding the model's behavior are explicit. The evolution from RLHF to DPO to constitutional AI reveals a clear trend. It's a journey away from direct, granular human oversight and toward more automated, scalable, and principles-based methods of control. This shift is driven by the sheer economic and logistical impossibility of using human labelers to keep pace with the exponential growth of model size and capability. But it also raises new and profound philosophical questions. Whose values get written into the Constitution? And can we truly trust an AI to supervise itself? As these powerful models have matured, a strategic and philosophical schism has split the AI world in two, creating a fundamental debate about the future of the technology. The battle between closed-source and open-source models. On one side, you have the closed-source titans, OpenAI with its GPT series, Google with Gemini, and Anthropic with Claude. These models are proprietary. Their architecture, training data, and the model weights themselves are closely guarded trade secrets. Access is typically provided through a paid API, where users can send inputs and receive outputs, but have no visibility into the model's inner workings. The case for this approach is clear. It offers enterprise-grade reliability, security, and ease of use. Companies can protect their intellectual property and monetize their massive research and development investments directly. The downside for users is a lack of transparency. These models are black boxes, as well as high costs and the risk of vendor lock-in, where a business becomes completely dependent on a single provider's platform. On the other side is the burgeoning open source movement, championed by companies like Meta with its Llama models and French startup Mistral. These organizations publicly release their model weights and sometimes even their training code. This allows any developer, researcher, or company in the world to download, inspect, modify, and run the models on their own hardware. The advantages are immense. It democratizes access to powerful AI, fosters a global community of collaborative innovation, and gives businesses complete control over their data and infrastructure, often at a much lower cost. The risks, however, are also significant. It requires substantial in-house technical expertise to deploy and maintain these models, and it raises serious safety concerns about the proliferation of powerful, unregulated AI that could be fine-tuned for malicious purposes like generating misinformation or hate speech. This is more than just a debate over business models. It's an ideological battle for the future of our digital infrastructure. The last 2 decades of the Internet have been defined by the rise of large, closed platforms, social media networks, mobile app stores that centralize control and data. The closed-source AI model is a continuation of this paradigm. The open-source AI movement, in contrast, represents a pushback toward the original spirit of the Internet, a decentralized, accessible ecosystem where innovation can happen anywhere. The outcome of this struggle will determine whether the next layer of technology is a set of privately owned utilities that we access on a pay-per-use basis or a shared, open resource that anyone can build upon. Perhaps the most mind-bending and controversial topic in AI today is the concept of emergent abilities. As researchers have built larger and larger models, they've observed a strange phenomenon. While many capabilities improve smoothly and predictably with scale, some abilities seem to appear out of nowhere. A model might show near-zero performance on a task like multi-digit arithmetic, and then, after crossing a certain threshold of size and training data, its performance will suddenly and sharply jump to being highly accurate. These emergent abilities have been documented across a range of complex tasks that were not part of the explicit training objective, including solving logic puzzles, writing computer code, and even demonstrating a rudimentary theory of mind by inferring the mental states of characters in a story. This has sparked an intense scientific debate. Are these genuine sparks of reasoning a sign that we are on a path to true intelligence, or are they a sophisticated illusion? The illusion camp argues that emergence is largely an artifact of how we measure performance. Many benchmarks use sharp, all-or-nothing metrics, like whether a model's final answer exactly matches the correct one. These binary metrics can mask gradual underlying improvements. If a model's ability to perform a single step in a multi-step reasoning problem improves smoothly, that small change can cause the success rate on the entire multi-step problem to jump dramatically, making an ability appear to emerge suddenly. When researchers have re-evaluated these tasks using smoother metrics that give partial credit, the sharp jump often disappears, revealing a more predictable scaling curve. Other researchers argue that these abilities are not true reasoning, but are simply the result of the model learning to perform complex pattern matching, or are a manifestation of in-context learning, the ability to recognize a task from examples in a prompt and apply a learned procedure. The other camp, however, believes that something more profound is happening. They argue that these emergent abilities represent a genuine phase transition, a concept borrowed from physics. Just as gradually cooling water doesn't change much until it hits 0 degrees Celsius and abruptly freezes into a solid with entirely new properties, increasing the scale of a neural network can cause it to cross a critical threshold where it can support new, qualitatively different computational circuits, unlocking new capabilities. This debate cuts to the heart of the biggest question in AI, the path to artificial general intelligence, or AGI, a hypothetical AI with human-level cognitive abilities across a wide range of tasks. Is simply scaling up the current transformer architecture, more data, more compute, more parameters, a sufficient path to get there? Or are there fundamental components of intelligence, like genuine causal understanding, consciousness, or autonomy, that are missing from the current paradigm and will require entirely new breakthroughs? We simply don't know the answer. As we push the boundaries of scale in pursuit of more powerful models, we must also confront the immense and often unseen costs of this technological arms race. The environmental toll is staggering. Training a single large language model requires a colossal amount of energy. The training of GPT-3, for instance, is estimated to have consumed over 1,200 megawatt-hours of electricity and generated more than 550 tons of carbon dioxide, equivalent to hundreds of transatlantic flights, and that's just for training. The energy consumed during inference, every time millions of users ask a question, is now believed to account for over half of the total life cycle emissions of these models. Globally, data centers are projected to consume as much electricity as the entire country of Japan by 2026, with AI being a primary driver of this demand. The economic costs are just as formidable, and they are leading to an unprecedented concentration of power. Training a frontier model costs hundreds of millions, if not billions of dollars, an investment that can only be made by a handful of the world's largest technology corporations. Microsoft, Google, Amazon, and Meta, these companies control the three essential ingredients for modern AI: the massive datasets, the vast cloud computing infrastructure, and the capital to fund the research. This is creating a new geopolitical landscape where control over AI capabilities is seen as a critical source of national and economic power, and the frontier is already moving beyond language. The latest models are becoming truly multimodal, integrating not just text and images, but real-time audio and video streams. The goal is to build an echo that reflects not just our language, but our entire sensory reality. So where does this leave us? We've journeyed from simple, rule-based chatbots to planet-scale neural networks. We've seen how a single elegant idea, attention, unlocked the ability to create a mathematical echo of human language with breathtaking fidelity. This universal echo can write poetry, debug code, and translate languages. But as we've seen, it is not a mind. It is a system built on statistical patterns, not understanding. It is shaped by the data we feed it, reflecting our brilliance, but also our biases, our creativity, but also our conflicts. It is tuned and aligned by our preferences, yet the methods for doing so are a battleground of efficiency, control, and philosophy. The echo is getting louder, clearer, and more capable every day. It's expanding to reflect not just our words, but our sights and sounds. And as we stand on the precipice of this new era, the ultimate question remains: As we continue to build this ever more perfect mirror, what will we learn when we are forced to truly see ourselves?
You've been listening to First Principles. Until next time, stay curious.